Good morning. Are you able to see the screen? PPT?
Yes, sir.
Yes, sir.
Okay, thank you. So, we will today complete the essay engine because we need to cover lot of portion because fundamentally I was taking a little more in depth, trying to make you to understand because students are from other departments also, not from the mechanical. Yesterday we looked into what we call as electronic throttle control because fuel injection is first step for making the engine electronically controllable instead of mechanical carburetor. Next term is controlling the throttle itself instead of driver pedal. Correct? Driver is going to press the driver pedal, but there's no mechanical linkage which is going to open throttle valve. That is controlled by a DC motor connected to a throttle valve, which in turn is controlled by electronic controller. The controller receives command signal from the throttle pedal. There's no mechanical link. Throttle pedal will be there. It is spring loaded. Then below there will be a sensor which measures how much the throttle pedal is pressed. That will be given as input. The electronic control generates voltage, which in turn control we saw yesterday. Then also we saw about modeling the mean value engine. Correct? We are talking about if you want to do modeling of the engine, SI engine, because now we call what we as a mechatronic way of designing system. Mechatronic way of design in which mechatronic system design. Any mechanical system which is controlled by electronic software, all those things can be modeled, and you can create what you call a transfer function. And from the transfer function, you can always correct. You can always create synthesize the controller development, or synthesize controller or controller development can be done. Correct. So, for example, we need a closed loop PID control. We call closed loop PID control, air field ratio control, PID control. PID control is nothing but proportional integral derivative control. You can have, there are many things. P controller is there, I controller is there, PI controller is there, PD controller is there, correct? Apart from these are the most widely used closed loop control system, very, very popular last more than 100 years, or at least 80 years, very popular closed loop, which makes the output to follow the input. If you talk about closed loop system, we know that there's a system, it's a mechanical system, which is controlled by a controller, electronic controller, and develops control signal, and that is given in the system. Part of the system is your actuator. Correct? Actuator is part of the mechanical system. Mechanical system fitted with actuator. Correct? So if you talk about engine, fuel injector is the actuator. Correct? If you talk about the fuel injector is the actuator. Fuel injector is an actuator. Another one is throttle valve. We saw that throttle valve is motor. Correct? This motor, the servo motor, which is going to control this is also an actuator. This is also an actuator. Similarly, the fuel injector, correct? That also is an actuator. These actuators are controlled by electronic controller, correct? So there are two electronic. This is for fuel injection control. This is for throttle position, air control. Throttle position is when you are going to control mass of the air, and this is going to control mass of the fuel, correct? So they are mixed already. We saw that. This is how it is done. When we talk, so now, if generally previously, before advent of the computer, digital computer, we are talking about digital computers, correct? Digital computers, invention of digital. Please note that first the digital computer is anywhere, correct? ENIAC is the computer by Bell Laboratories in US, correct? Bell Lab US is developed ENIAC computer. Then came UNIVAC. Like there are many computers. These computers are all called mainframe computers. Please note that generally, if you see that this one, you make a single cylinder SI engine, or for example, petrol engine, auto, correct? Auto developed the single cylinder petrol engine, single cylinder small engine, that is called prototype. First invention will be very small, correct? You won't make big one, whether it will work or not. You won't make a first engine, it's a multi-cylinder. 10 cylinder, 12 cylinder, something like that. Whether diesel, Rudolph diesel or auto, any Thomas Alva Edison, anybody develops this always a small prototype. If it works, they try to improve like that. But unfortunately or fortunately, the computer developed, correct? The computer alone is a reverse. Computer field, computer science, or computer which talks about hardware, software, all those things. First computer anywhere is a big computer measuring something around a big room size. Correct? Measuring something 6 feet wide, some 10 feet tall, like the big racks. Okay. So each involving kilowatts of power. They are using what you call vacuum tube. They call it a vacuum tube. That time transistor IC was not there, correct? This is around 60, 80 years before. Vacuum tubes, which is called as valves, electronic valves. They call it as electronic valve, measuring around something around 3 to 4 centimeter height, sometimes even 8 to 10 centimeter height, correct? It is cylindrical shape. It will be something like this, and there will be pin inside that, the anode, cathode, all those things. This size may be even 6 to 10 mm. 10 centimeter, and the diameter may be 2 to 3 or 4 centimeter. Like this, they will be using thousands of valves, correct? This valve, one valve is equal to one transistor, correct? Transistor nowadays, you know that is very, very small, measuring only this big, correct? Which is using this one. Now, this is, if you take your Pentium processor, this is a transistor, correct? Transistor occupies this big, correct? It has 3 legs. Correct. So if you see physically in your computer about all these things, this is a big. Then with the advent of VLSI technology, very large integrated technology, all these things. Now in your i7 processor or i5 processor, you have 10 million transistors in 1 cubic, less than 1 cubic centimeter, or well maybe less than 1 cubic inch. 10 million transistors, correct? Packed. So when the first computer was there, they were using vacuum tubes. That computer required around 10,000 vacuum tubes, valves. Correct? And they work with 300, 400 volts, and there's a heater inside to emit electron, thermionic valve. They call thermionic valve. You supply current, there's a tungsten, this one, like a bulb, no? Incandescent bulb. You supply current, it gets heated up, the cathode gets heated up, it emits electron. There are anode, all those things. So that's how it was working. So you have to put 10,000 valves, but each will be getting a temperature up to 300, surface temperature valve you can't touch. Maybe something 80 to 90 degree. Valve will be very hot after the 10 minutes. Because if you have old radio, because in my house I had a radio. My father bought, which is a Philips radio from Holland. I'm talking 50 years before, correct? So you switch on the radio, after there will be 6 or 7 valves, because it's not transit radio, it's a valve based. After 10 or 15 minutes, if touches the surface of the radio cabinet, you can see it will be very warm, correct? So 5 to 6, we are talking about 10,000 valves in the any computer, first computer. So it was a big size. They had a cooling fans, all those things. Better that the valves, if overheated with no cooling, is the valve will burst, correct? Because it is bulb, it is to so many valves very close. Sufficient cooling is there. Overheated glass bulb will, the outer wall of this is made up. See, the valve is made of glass bulb, correct? They will break. So that's not our interest. So now the initial computers were big because of valves they use, but later now you have your palm top computer, your cell phone, which has a i3 processor equivalent, correct? Or i5 processor equivalent power in your cell phone itself. The CPU has not only cell, you can do the calculation, you can install Windows, all those things, correct? If you see Nokia cells, all those things, you can install Windows itself. Right? Microsoft also released some computer, all these things, cell phones. Okay, so because of that you can do. Now there are 2 electronic controllers which is going to do this, correct? So initially when you wanted to develop controller, you make an engine, put the injector, all this thing, manifold, 3 TPS, all these things, then the control unit. This controller, correct? These 2 controller can have closed loop control, correct? Closed loop control consist of PID controller, PD controller, PI control, depending upon what your requirement, correct? So inside this algorithm, how this is implemented is a software algorithm, correct? It can be implemented using hardware also, correct? PID control can be implemented using hardware, which is nothing but analog computer. It's called as analog computer, correct? Analog computer consists of what is called operation amplifier, op-amp, correct? Short, it is called operational amplifier. It's a special electronic device, correct? It is a special electronic device, which is short form is op-amp, correct? So op-amp using that you can build this one. PID control you can build, correct? But instead of that, if you wanted to, because modern day computers are digital computer, because this is called digital computer, correct? These are all digital computers, which has microprocessor, microcontroller, in which the control algorithm is developed as software, correct? Control software algorithm is written as a software. Advantage, you can change the algorithm by replacing the new program. If the old algorithm is not working, some is a bug in it, what do? You delete that, because it's stored in your memory, EEPROM or something. You delete that, again write a new program, put it. Same hardware, because the digital control computer also needs CPU, memory, correct? All this input, output, all are electronic ICs. This is called hardware. Inside it, you are going to store the software, including your operating system, application program, your maps, all those things. So by changing software, you can always reprogram the controller. Correct? That is advantage of digital controller. Digital control easy, correct? For example, Mars, Perseverance robot was now deployed by the Americans in Mars, last week, and India also, Mangalyaan, we said. They all have digital computer. Suppose the rover, correct, is not working. The robot arm is not working. What you can do is, in fact, we are doing, correct? Americans and NASA is doing, ISRO is doing. You can send a new program, erase the old program which is stored inside that Mangalyaan or Perseverance or Curiosity robots, which is a wheeled robots, reprogram it, make it work. That is the advantage. Reprogram. One of the most important function, correct, compared to analog. But analog computers can be developed using operational amplifier. All these things, correct, PID control, any controller, anything can be, but it is a little more complex because everything is implemented through this one, operational amplifier, capacitor, resistor, electronic hardware. But once you deploy, suppose in the Perseverance robot Mangalyaan, if you use analog computer, while testing it may work here. But once it is deployed remote place, you can't. Only way to reprogram it, you remove the components. You remove the resistor, transistor, IC, all those things, put a new component with new value, then only you can reprogram, make it work differently if it is not working. So it is a hardware change needed. So that means you should have physical access to the system. But Mangalyaan or Perseverance, which is around 3 billion kilometers away, you can't reach over. If there is some mistake, and if the system is not reachable by humans, you can't service it. You can't make it all right. But the digital computer, if hardware part is okay, but please note that if your CPU or memory is failed, even in digital computer, over. If hardware failure means the end of the. But if it is software, you can reprogram it. Correct? So that is under. So we are trying to, what we are trying to do here is trying to develop, because all our ECUs, electronic control units, are digital controllers. They are using microprocessor, microcontroller. Okay. Now, what I want to say is, if it is before advent of advanced computer, simulation software, modeling software, you have to do everything physically. You have to develop physical engine, physical hardware, correct? So ECU you have to develop, correct? ECU1, ECU2, both you have to develop, write the program, store it, connect to injector, connect to DC motor, and conduct the experiment. And if it is not, then you have to make the corrections, changes in software or hardware, and make the engine to work as per your vision, correct? Required speed, omega or theta or torque. This is what the engine output. So to achieve whatever you need, torque or angular velocity or position of the motor, generally we are not interested in engine, correct? Engines are generally trying to drive, correct? So but omega is nothing but rate of change of theta. So this is the output. So for that we can program. But now, before building all this thing, now mechatronic way means you don't build the system. First make a model of the whole system, correct? And what is the model? Mathematical equation. It is called mathematical equations, correct? These equations should be written as a program, converted into a program. The equation will be converted into program, correct? Computer program, correct? Those programs can be written in C, Java, or Fortran, correct? Or whichever software you want, correct? Or MATLAB, correct? You can write any software, and after that you will be able to make this one to run into your computer, correct? So this mathematical equation represents the system, correct? Yesterday we stopped here. Where did we stop yesterday? Hello, did we talk about this yesterday? This part?
Yes, sir.
Manifold, all those things. Okay.
We came to the equations.
Yeah, we came to equation. Thank you. Okay. So now what we want to say is, because this is what the variables were correct, which is going to come to decide what is the lambda. This is airfield ratio control, correct? Lambda, we wanted to see how to control the exhaust airfield ratio by varying the parameter, like ambient. This is ambient pressure, you cannot vary. This is ambient temperature, you cannot vary, but you can vary the throttle, correct? And throttle angle. So the mass of the airflow rate going inside the manifold can be controlled by controlling throttle angle. Once you control it, then this is the Manifold is a storage device. It is a storage device. The manifold volume decides what is the pressure inside the manifold, air pressure, temperature, and mass of the air entering into manifold. Correct. That depends upon the throttle opening alpha. From manifold, further the air is going inside the cylinder, combustion chamber, because the vacuum is created and piston is going down. So that time the amount of the mass of the air entering into the combustion chamber, which is called M-AP, is decided by this opening of the valve. Correct. This pressure, P manifold, P temperature, and also the vacuum here. What is the vacuum? Correct. The pressure inside the combustion chamber. Correct. Inside the cylinder. Combustion chamber, okay. PC decide. So you know that only when there's a pressure difference, the air will flow, fluid will flow. That means PC should be lesser than P manifold. So the air enters from the manifold, which is from the atmosphere, it is sucked in based on how much throttle angle. That mass of the air past the throttle is M-AT. Correct. That depends upon the P manifold and the difference between P ambient and P manifold. Correct. That difference. Similarly, temperature inside the manifold, atmospheric temperature. These two decides how much mass of the air will enter into the manifold. That is called as mass of the air pass through the throttle. That is AT. We have put subscript. Correct. That depends on throttle angle. Similarly, the vacuum and the opening. How much this is opening? Correct. So this gap. And this cylinder, the inside the cylinder pressure, I say PC and P manifold, difference in between decides, and the temperature and the temperature of the this one air inside this cylinder, the combustion chamber decides. Correct. So that is called, that decides this one, how much air mass will enter into combustion chamber when vacuum is created. From here, after combustion happens, then burned exhaust gas pushes the piston down. In exhaust stroke, it will be thrown out. So finally, this is three-way catalytic converter. You have the lambda sensor, correct? Lambda sensor, EGO, exhaust oxygen. This measure what is the actual air field ratio of the combusted product, correct? Leaving out, correct? We know what is the lambda here, correct? Lambda here, we know that is here, especially here after injecting the fuel, correct? This place you know the lambda, correct? Before combustion. Amount of air you know, you are injecting this required fuel quantity, then lambda you know. AFR is nothing but MA divided by M fuel. Correct? So you know that. Now combustion happens. After combustion, some amount of air may be, oxygen may be still left over. Because of that, there's a this lambda sensor checks. Correct? Engine outlet, lambda outlet, correct? Which in turn is measured by the sensor. Then three-way catalytic current sense. Now here you can model. Correct. So intake airflow model, there are two things. One is air dynamics. Correct. Airflow dynamics. I can say the airflow dynamics. Other is fuel flow dynamics. There are two things. Airflow dynamic depends upon these things. That's what we saw. Correct. That's what we saw here. Correct. So air enters. These parameter decides throttle angle, manifold pressure. So manifold pressure and temperature, what is size of the manifold, volume of the manifold, all those things. So all the parameters going to do. So that's the equation shown here. Correct. So the pressure, rate of change of pressure at manifold. Correct. As the piston is moving down, the pressure inside the manifold is not going to be done. It is going to vary. There's a P dot means rate of change of pressure. That depends upon the R. Correct. So then T manifold, V manifold, volume of the manifold, air temperature inside the manifold, and R is the gas constant, you know that. Then this is nothing but mass of the air flow rate, correct, mass flow rate of the air after the throttle valve, correct, from the atmosphere, minus the mass of the air inside the cylinder, correct, mass flow rate inside the cylinder. If you know this, you can find the manifold pressure change, correct. Based on that, then you will be able to find out mass of the air passing through the throttle valve is nothing but M-AT, correct? This one, this air, that depends on this throttle angle and this and this. That's what equation is given here, correct? Is nothing but mass of the airflow at this one throat multiplied by P atmosphere ambient into root of T ambient into B1 is the function, which is a function of alpha. Alpha is nothing but throttle angle, correct? Alpha is nothing but throttle angle. Similarly, B2 is another function, which is the function of PR. What is PR? PR is nothing but manifold pressure divided by inlet, the pressure at inlet valve. P in means pressure at inlet valve. Correct? This is manifold. Why? Because here there's a restriction, correct? Here there's a volume, here there's a restriction, again there's a big volume. In between, the pressure difference will happen. This is a P in. This where the pressure at the inlet valve, correct? Inlet port, correct? That's what this equation shows, correct? So then what is beta 1? Beta 1 is a function of alpha, throttle angle. That is given 1 minus A1 into cos alpha, again cos of the throttle opening, A2 into cos square alpha, again throttle angle. So then what is B2? B2 depends upon PR and PC, correct? If PR is greater than or equal to PC, PC is nothing but pressure inside the air pressure inside the combustion chamber, correct? Is equal to PR is greater than or equal to P. This one, you can use this equation to calculate B2, correct? So similarly, if you put if the PC is smaller than PR, correct? PR is smaller than PC, then you can consider B2 equal to constant 1, correct? This part will become 1, correct? So then what is PC? Because we are talking about PC inside the combustion chamber, pressure inside this one. Is it divided? Is nothing but P1 divided by P2 whole power 1 divided by P2 minus P1. What is Pn? Here we are talking about Pn, correct? In this equation, the Pn is nothing but root of PC power P1 minus PC power P2, correct? So these are the modeling. I'm just trying to explain how we can, even without building the system, we can develop the airfield ratio model, which is called mean value model. From that, you can always find the how this airfield ratio can be controlled. Then you can develop controller also using MATLAB simulating some software, correct? This is called modeling and development of controller. So the airfield, now this is the modeling part we are talking. Then how will you develop the airfield as a controller without developing field? Because I am talking about modeling, correct? So you can see here this picture. Quickly we'll go through. This is the fuel is injected. There are two paths. I told air path, correct? This is fuel path. Correct. Please take the notes, the functional block diagram, because in exam you may expected to show what important parts. Correct. So take the functional block diagram, because I am not changing slides also quickly. So the air path is this, the fuel path is this. In air path, what is the air path? The finally cylinder air mass. Correct. Cylinder air mass. Cylinder air mass. Okay, cylinder air mass depends upon intake dynamics, correct? The intake dynamics is nothing but intake dynamics, what we have explained here. The whole thing, correct? The whole thing from here up to this, correct? This variable using this equation already we have written intake dynamics. This is a air intake dynamics, correct? Intake dynamic model, the whole equation, this equation, correct? The amount of the mass of the air inside the cylinder. Correct? So this is past is this one. Finally, the equation is given here as air dynamics. Air dynamics is nothing but mass of the air trapped inside the cylinder. Correct? Trapped inside the cylinder. This one. Correct? So the air passes through restriction of the throttle. Correct? Then some amount of mass is going. Correct? When throttle open, depends on the throttle angle, which in turn is stored inside the intake manifold. Then from there, the air enters in the combustion chamber as the piston is going down. Finally amount of the air sucked inside the cylinder is not same as mass of the air pass through the throttle plane. Correct? Because air has a mass, it has a velocity. The velocity and mass, all those things depends upon pressure and temperature at various points. Correct? That is what is shown here. These equations are showing those are the equations how you can calculate. Correct? So now intake manifold is the finally rate of pressure from here, because the air is coming from manifold to combustion chamber. So this pressure, P manifold pressure, plays a vital role whatever atmospheric, all the things decides how much the air will enter into the manifold and stored here. Due to that, there's a pressure of the air. That is manifold air pressure, and it has a temperature. Correct? Because while it is going through when moving, when pressure changes, flow rate changes, the temperature also. This temperature will not be same as ambient temperature. Correct? Ambient temperature 30. Correct? The T manifold, the air stored inside will not have same because it is throttled. Correct? The throttling is pushing something in through a narrow path. The who is pushing? The piston is sucking. So because the air atmosphere pushing, it is pressurized. Correct? When it comes here, pressure increases. Here there is some pressure. Here there's a pressure in between. It is pressure because it's going through narrow channel. So the temperature also vary. Correct? Pressurized when expand automatically the temperature. So T, we know that T in ambient will be greater than T man. Correct? Which in turn again through a restriction wall, all these things, again the air entering. So that's what manifold dynamics. Correct? We are so here air path is decided by these equations. Correct? Amount of air entered into cylinder. Correct? Which is called as mass of the air flow rate inside the combustion chamber. Correct? Is this now for which you are depending on airfield ratio AFR, you are going to mass of the air, you know. Flow rate is there, dash is there, correct? Inside the similarly, you have to inject fuel injection. Correct? So rate or mass directive control. So how it is controlled? That is by injector. The injector, this is the fuel injected by the injector. Mass of the fuel injected are commanded. FCMD means commanded. Who is commanding? ECU. How ECU conduct? ECU measures the MAT, correct? So this is measured, correct? MAT is the based on throttle angle. The ECU will calculate how much mass of the air passed through the throttle, and then if you know the temperature, correct? Ambient temperature, then you will be able to calculate this, the volume and pressure. Based on that, you calculate the mass of the air passing through throttle plate. After that, you can find out. Then based on that, you know how much further the equation. Based on these equations, correct? Using this equation, you can find out what is the finally mass of the air entered inside the cylinder at end of suction stroke. End of suction stroke, valve is closed. Correct? All the air, correct? All the air entering, correct? The air entered here, mass of the air, correct? I say admire this one, will not be inside the here. See, this will be different, this will be different. Why? Because air has a mass, correct? And it is flowing, and temperature difference, pressure difference, all those things decides the final, when the valve is closed, end of the suction stroke, the valve is closed, the air is stopped entering. That mass is M-AP will be lesser than this air, correct? M-AT will be definitely greater than M-AP. Why? Because restriction, all these things, flow rate, by that time valve closes, air was coming, by that time inlet valve is closed, suction stroke was over. Because air has a mass and velocity, all the mass which came here will not be able to enter. So that's why we call a volumetric efficiency, amount of the, if you talk in terms of volume, you say volumetric efficiency, correct? That depends upon engine speed, correct? The piston speed, correct? It is called piston speed. That depends upon engine RPM, how the crank is rotating, correct? Omega, correct? If the engine is running faster, volumetric efficiency is always less, because valve quickly closes on this one. When engine speed is less, volumetric is generally high. You will be knowing that is not our that is separate area. Okay. Now the fuel dynamics. You inject the fuel will be injected where? I will show you the old one. Correct. So here, for example, I am running this engine at 3000 RPM. Correct. At say 25% throttle. Correct. For that, I want to maintain airfield AFR equal to 15:1. Correct. That means if 15 gram of mass is going in, 1 gram of fuel should be injected. Correct. So this is measured using throttle position sensor. You are measuring some sensor using that. You are able to find out what the mass of the flow air entered into the cylinder. Okay. Then the ECU will inject 1 gram of fuel. Correct. This is the air mass in grams. I say that, say 15 grams. Correct. Then fuel injected. Who is going to the ECU? ECU already knows amount of air going, all this thing using the airflow sensor, and it is calculated because you asked the ECU to maintain airfield ratio 15:1. That is a commanded value. So this 1 gram is the mass of the fuel commanded CMD. Correct? How? By giving a pulse width. For example, the injector open the injector for 1 millisecond. Correct? For example, it opens 1 millisecond. So it is 1 millisecond is the duration of the pulse. Correct? Injector opening pulse, which is called this one. Then I say 1 milligram fuel is injected. When I open the injector, that's how the injector is there. Already you calibrated. So now, if we inject the fuel 1 milligram, correct? So some amount of fuel is going inside because the inlet valve is on, air is going in. You can see that it will evaporate, go, correct? Because the fuel missed. But still, some amount of fuel is, you can see that it is touching the manifold. This is manifold valve, correct? So that is called fuel puddle. That's a liquid fuel. Correct? Remaining fuel are evaporated, went inside. So I say that some 10% of fuel is sticking here because the injector you cannot make exactly spray only inside the engine, this valve, outside the valve. So some fuel may be touching it. They're called fuel puddle, which is called a valve wetting. Correct? We know that is valve wetting. So the 10% fuel is sticking, remaining 90% went inside. Correct? But this fuel which touch the valve will not. There's a liquid. This fuel puddle means a liquid form. Correct? The 10%. So what is that? 0.1 milligram. We injected 1 milligram. Injected 1 milligram. Out of that, 90% means 0.9 milligram fuel is already went inside the engine along with the air. Remaining 10%, which is 0.1 milligram fuel is sticking here, but that also will evaporate as air is going. Correct? Air is entering air, say for example 30 degrees something. It will also slowly the fuel puddle, which is nothing 1 milligram, which is nothing 10% of the fuel injected to maintain 15:1 airfield ratio. Correct? If you wanted to maintain 15, already 15 gram, say for example, 15 milligram air went inside. Correct? I am telling you that. So then I have to inject 1 milligram of this is air. Correct? Air is already inside the cylinder, trapped. Or while going along with this. Now, if you inject a 1 milligram, all the fuel should go inside the combustion chamber. Then they mix together, then air-fuel ratio will be same. But now, some fuel is sticking here. Air is went inside with 90% of fuel. Correct? 10% fuel is sticking here. Correct? That fuel also is evaporating going. By the end of the suction stroke, when valve opens, maybe 0.05 milligram fuel is not evaporated. Still, it is liquid form. Correct? So that means what will happen? The amount of fuel went inside your cylinder will be lesser by this much quantity. Correct? 0.5. Yeah. So the 0.95. Correct? Gram of milligram fuel only went inside. Remaining 0.05 milligram is sticking here. Now valve is closed. So the air-fuel ratio is still linear. Now inside the air-fuel ratio, because you have 15 milligrams of air, but you have 0.95 milligrams of air only went inside the cylinder because of valve wetting. So the actual air-fuel ratio is not 15. It will be higher than higher means it will be linear. It may be 16. Correct? 16:1. So that means next time you have to change. Correct? Dynamically you have to change the fuel quantity. So to consider the valve wetting phenomenon. So that can be done using this equation. Correct? So this is the equation. You inject this is fuel injected, commanded. I told you 1 mg. Correct? 1 mg fuel is being done here based on this equation. In this is called as tau. So you can see that this is nothing but tau J. Tau J is nothing but time constant of fuel evaporation rate. Time constant of fuel evaporation rate. Correct? All the fuel, you inject a 1 milligram, 0.1 milligram was sticking to the valve wetting. But the fuel is evaporating as the air is going. Correct? So how much fuel will be evaporated, that can be calculated using this equation. Correct? Now, both the air and the fuel is went inside, fuel mass is right, they mix it together, combustion, you're giving a spark, combustion happens. Once combustion happens, correct? Combustion doesn't happen instantaneously. You give a spark from the spark plug near the spark plug point, correct? Combustion starts, correct? Combustion starts near the spark plug. Spark is given near the, as I told you that this is suction stroke. then it goes, then it comes down, it goes up, correct? Here you are giving the spark. This is the compression. This is the suction. This is the power. This power stroke. This part is exhaust, correct? So in the compression stroke, just near this one, you're giving a spark. Where? Here. So that means here combustion starts. Then the flame will propagate because the piston is going down, volume is increasing, flame, the fuel air mixture will be burning. Some amount of time. So fuel air to mixture to burn, it takes some amount of time. Correct? All the fuel will not burn instantaneously. If the fuel is burning instantaneously, it is called detonation. It is called as detonation. Correct? Detonation is dangerous. Correct? That means all fuel are burning, then high pressure will get, it is also called as knocking. If all the fuel burns instantaneously, correct? Once a given spark, immediately if it burns, it cannot happen. We know that if you have multiple hot spot, because I will tell you what is a hot spot, then fuel can burn instantaneously. It is called detonation because of knocking. Knocking means the cylinder will vibrate, correct? Violently vibrate, and the engine cylinder can break. If you run your engine in knocking condition or detonating condition, engine will fail. So you should not run the engine at knocking condition. Okay, that is separate area. If you are ice engine people, you will be knowing. Okay, in this, now we give a spark, then flame propagates. So to burn all the fuel, it takes some amount of time. Time for combustion. Correct? Time for combustion. The fuel burn as this one. So that will be in the milliseconds. Correct? That will be milliseconds. Then the suction, the exhaust stroke. After the power stroke, piston came down. The suction stroke, the exhaust stroke, the exhaust valve opens. The hot air is going out. Correct? The air, that is nothing but the hot air, combusted this one, will be going out and goes to the. So from here, this is a gas, hot air is moving and goes into the TW converter, three-way catalytic converter. Here you have your sensor, correct? Exhaust sensor, exhaust arc sensor, EGO, which measures this one. So the hot has to come here. So this may be 1 feet length, correct? To travel 1 feet, the exhaust gas, hot air takes some time, correct? So that is called exhaust time delay. That is called exhaust dynamic delay, correct? So then the sensor, the hot air touches, the hot gas touches the pass over the EGO sensor. EGO sensor measure the amount of the oxygen or air fuel ratio of the exhaust. That to sense that sensor also takes some amount of finite amount of time, correct? So that is called as exhaust gas sensor time delay or sensing time delay. So all these things included in your model, correct? So you can see that this is what time delay. One is transmission, that is exhaust gas moving from combustion chamber to the exhaust sensor. For that, there's a time delay that is called this T. It is not temperature. Please note that this is a time in milliseconds. Correct? That is for exhaust gas to reach from the combustion chamber to the sensor. Correct? Sensor may be located 1 feet away or 1.5 feet away from the outlet port. Correct? So that time. Then this time TC is nothing but combustion delay. Correct? Air fuel is not mixing instantaneously. It takes some millisecond to burn. So due to this, a time delay. So that time delay is represented e power minus TC plus this one into S. Then this gas mixes, correct? The exhaust gas mixes all those things, correct? Inside previous, correct? Inside this is your three-way catalytic converter. Three-way catalytic converter does some volume. Inside that you have catalyst, all those things. So in the previous exhaust stroke, some amount of gas came. Then they went to pass to then added to atmosphere. But some amount of residual gas may be inside the TW converter. So the first exhaust gas mixes with old gas. So because of that, there is some time delay. The sensor time delay, mixing time delay, we call, correct? So time constant. So finally, this is the equation which shows what is the equivalence ratio. This is called an equivalence ratio. Correct? So lambda is called air fuel ratio, correct? Which is nothing but mass of the air divided by mass of the fuel, correct? So when we say air fuel is rich means it is 13:1, 12:1, 10:1, correct? Lean means 15:1, 14.7:1 called stoichiometric, correct? We know that. But it is generally when you say rich means it should be a bigger number, correct? When I say rich mix here, correct? When I say air fuel is rich, we know that it is lesser than 14.7 is to 1 is the stoichio, correct? Stoichiometric air fuel ratio, which is called reference. Lean, this is rich, correct? This is rich means lesser, the air quantity is less, correct? Fuel you are maintaining same one, air quantity is less, correct? That means more fuel is there. So you say 13 is to 1 or 12 is to 1. This is called. But lean means opposite, correct? Air is more, fuel is less. Say 15 is to 1, 16 is to 1. This is called lean. But it doesn't make sense, correct? Americans are saying what the British is saying is not correct. It doesn't make a sense. When I say rich, it should be bigger, so more fuel, correct? So they use what you call equivalence ratio. Equivalence ratio is given by psi is nothing but 1 by lambda, correct? So here they say if I wanted to maintain particular equivalence ratio at exhaust instead of lambda, they are saying equivalence ratio, which is nothing but mass of the fuel, correct? In the numerator it has mass of the fuel. Lambda equal to mass of the air divided by mass of fuel. Inverse of lambda is mass of the fuel divided by mass of the air. So in that case, you can say denominator in the equivalence ratio. When you talk about the equivalence ratio, we are always talking about in the denominator air mass m dash ap, correct? Inside mass flow rate inside the combustion chamber, correct, is mixed with some fuel. That is the numerator. That is nothing but 1 multiplied by the whole thing, correct? So you are here you are injecting fuel, correct, at the inlet port, correct? Then we know that some amount of fuel is sticking to as a fuel puddle, correct? 0.1%. For example, I told you, remaining 90% go in. The fuel puddle also evaporates. That is called evaporation dynamics, correct? The fuel injected is 1 milligram, correct? Then how much go inside? This is decided by this equation, correct? This depends upon the evaporation days, time. Tau F is fuel puddle evaporation rate, correct? Again, this is dynamics, correct? Time delays, exhaust dynamics, this all the time delays. If you multiply the whole thing, correct, which is called a fuel dynamics, and that's what this, correct? And this fuel is injected here, correct? Then some fuel is sticking in the wall, remaining goes inside. But even while going, some amount of fuel is going. This is fuel per cycle. This fuel will go, combustion happens. Then exhaust. There's a time delay. All those things they're given. So this is the equation for this. You can program, correct? You can write a MATLAB program, write a MATLAB C program. All those things using this equation. In this equation, if you are able to give these values, correct? Mass of the air went inside. You can do simulation, correct? You can write MATLAB C, all those things. You can find out if I wanted to maintain particular equivalence ratio, correct? For particular amount of the mass flow rate inside the combustion chamber, what should be fuel quantity? You can find out, correct? Or fuel injection rate, correct? Fuel injection rate, mass of the fuel injected at the inlet port. This you can find out. What is that? This is the mathematical model of air fuel ratio controller, correct? So these are mathematical. So you need not build the engine. Using this equation, you can change the mass flow rate, all those things. You can, so that depends on the throttle, correct? The mass of the air going inside depends on, already we saw the equations, correct? These equations, throttle angle, correct? Here also here, correct? Throttle angle, this diameter, correct? The manifold is something like this. Inside which you have throttle plate. What should be the radius of this one? What should be length? Then you have the manifold, correct? Some amount of storing again goes in. So you can find the dimensions of these things. Based on that and throttle angle, what is the opening, all these things, you can find out what are the masses. So you can vary this value, correct? This throttle opening, the diameter, all these things you can change and using computer program without building the throttle, without building the engine, without having the TP, the sensor, correct? Lambda sensor also can be modeled, correct? Lambda sensor also is modeled, already is given. This equation you can see here, correct? This is the lambda sensor equation. Lambda sensor first order equation, correct? So like that you can do. So you this by programming this, by varying these parameters, you'll be able to find out for this much of air mass entering inside my cylinder, correct? This much of air. If I inject this much of fuel, or if I want to maintain this much of equivalence ratio, which is 1 over lambda, what should be fuel quantity? I have to fuel quantity you can calculate. So fuel quantity can be, so you can select the injector size, correct? The pressure, all these things you can do. This is called model. Okay. So now, as I told you in the previous class, that if I wanted to open loop control lookup table based, if you open loop, see this how you do, you generate the fuel map. Already I told you about, correct? This is spark timing, correct? So you can generate, this is open loop control, this is N alpha method. This is N alpha method, correct? This is open loop control. You can see that once a table is created, this table is stored inside the ECU, correct? Then in the engine, you put the speed sensor and also you put the throttle position sensor, TPS sensor. So based on the TPS value, all these things, speed code and throttle, correct? There are two sensors, correct? The speed sensor and also throttle sensor. Those sensors measures the actual engine speed and throttle opening. Based on that, lookup table, the fuel will be injected, correct? And similarly, spark timing will be also calculated, correct? You can do that. So this already we saw. So you have to develop this 2 dimension. I told you there's not one table for different temperature, different speed, different altitude. You may have 30 to 40 tables, correct? Stored inside your ECU. But you will base the inlet air temperature and this one. You can select engine speed and throttle position. The ECU will select appropriate table, and depending upon the 10%, say 4,000 RPM, 4,000 RPM means it will open the injector of 1.569 millisecond. So that much quantity of fuel will be. So that will be used to maintain 15:1 air fuel ratio. I think I did this map for 15:1 air fuel ratio, if I'm correct, because I did more than something 17 years before, 16, 17 years before. This is my PhD work, I told you. Okay, so you can create. So then in closed loop sensor means I told you that you have your engine, correct? Your engine combustion chamber. This is your combustion chamber. This is your manifold where the injector is located, correct? The fuel, then the fuel, air is going in, fuel is injected, correct? They mix inside the manifold and enter into the combustion chamber, correct? Engine. Then spark is given, combustion happens, the exhaust goes. This is exhaust gas, correct? That goes through three-way catalytic converter. Finally, the treated. This is the treated exhaust. Treated exhaust means three-way catalytic converter. What it does? It converts CO, HC, and NOx into H2O plus O2 plus N2 and CO2. Correct? So all the noxic gases are converted into inert gas, O2, N2, and CO2, and maybe some water. That happens. Okay, that's what the whole idea. How it works? It uses a sensor, lambda sensor. Close to air fuel system, you have to measure the actual air fuel ratio at the exhaust. That is called lambda sensor or EGO sensor. These are different names, or exhaust gas oxygen sensor. So that gives information to ECU. What is the present exhaust gas air fuel ratio? Based on that, the fuel quantity is converted. Correct? You can see that fuel quantity is varied. So now, if you want to maintain 14.7:1, correct? If this is on type, correct? Fuel quantity on type, correct? So it may reduce. It is continually varying. The air fuel ratio going inside the combustion chamber is controlled by varying the pulse width. This is pulse width, right? So this is air fuel ratio measured by the exhaust sensor. Please note that this is the air fuel ratio measured by the sensor. EGO sensor signal. You can say that it says for some duration reach, again the engine become lean. Next cycle, again reach, next cycle lean. How it is made? By varying the pulse width, correct? Injection pulse width. So ECU does. This is called closed loop ergonomics. So this is how the exhaust oxygen gas sensor works. It is nothing made of zirconia. It is called zirconia material, correct? It has two plates, correct? So now, if exhaust gas flow, depending upon oxygen concentration, it develops millivolts. So this is the input-output characteristic of exhaust gas, correct? So depending on this is a stoichiometric, you say that this is lambda. Lambda equal to 1 means stoichiometric, correct? During stoichiometric, this sensor provides, depending upon the air fuel ratio of the exhaust gas, what it decides is it gives a voltage. The voltage value varies from 0 to 800 millivolts. That's what the exhaust EGO sensor, correct? It is called binary EGO. Why? When air fuel ratio is lean, the output will be this 50 millivolts. Correct? Consider around close to, in fact, they say 0 millivolts. Correct? So when airfield is rich, correct? Then what will it give? Around 800 millivolts, close to around. Correct? So that is the output of, you can see that this is sensor. The sensor output voltage will be 800 millivolts or 0 millivolts. Correct? So it is switching. So it senses. So when airfield is exactly at for this one, it is supposed to give around 400 millivolts. Correct? But you can see that the output voltage switches when airfield is very small, narrow. So that's why it is called binary. Correct? Based on this is the sensor data. Based on the injector fuel pulse, which is varied, the airfield is controlled. Correct? So now, because I want to close these engines, correct? So next class, I want to start diesel engine quickly. Correct? There are two ways. One is called lookup table. Correct? To maintain the, so this is closed loop airfield. Correct? This is closed loop airfield using exhaust sensor. You can see the EGO sensor, which checks with what is set point. I said 15:1. This is my set point. Correct? So that is compared to the actual value measured by the sensor engine. This is exhaust. It measures. So based on that, the delta W pulse width will be varied. Correct? That pulse will be added with base pulse width. What is base pulse width? Base pulse width depending upon, see here also 15:1 only, or it can be stoichiometric. For that, you have the lookup table. Correct? Lookup table, what is that? Engine or throttle percentage versus RPM. Correct? So already we saw this table. Correct? This table is there. That is for open loop. So generally in most of the engine, actual engine, you have base fuel width. Correct? I told you, if I wanted to maintain this 4000 RPM, 10% throttle in the particular engine which I did experiments, we are supposed to inject 1.569 millisecond. Injection should open. Correct? So that's what we here. For this here, 1.569 millisecond injection will open. The pulse will be like this. Correct? Then this, when you inject that, this duration, injection pulse is this much, the fuel is injected, combustion happens, exhaust comes out. But sensor says that it is lean. Correct? So the actual airfield is leaner than what I said. Correct? With the 15:1. But now it is 15:5:1 is there. That's what sensor says. Correct? Immediately what this will do, this airfield is a closed loop controller will calculate how much fuel should be added. More fuel should be added compared to already. So that means pulse width should be injected. It calculates. For example, it says that 0.1 milliseconds should be added addition to bring back from the 15.5 to 15.1. So you can design, correct, closed loop control. So that means the delta W will be 0.1 millisecond. So I will be adding, I will show it in another color. You can see that my pulse width will be increased by, this is 1.569 original pulse width. The closed loop airfield says that now airfield is not 15:1, it is leaner, because already you said here, you say 15:1 is the set point. Correct? Now actual measure is still lean, 15.5. So it says that you have to increase the pulse width by 0.1 millisecond. This pulse width is 0.1 millisecond. So in the next cycle, what the ECU will do, it will inject not 1.569, it will inject 1.69 signal, that is 1.669 millisecond. This bigger this one. So again, that means more fuel is going in. So this pulse width here is more compared to previous cycle. Combustion happens when it comes out. So the sensor says that no, the airfield ratio is not 15:1, it is say 15:0, 15:1. It's a 15.2 this one, or say 14.9, which it says. Correct? If the airfield ratio is 14.9:1, when I inject this pulse width, so that means I inject more fuel. So the exhaust sensor sense measures. So immediately what this will, it will reduce from base pulse width. Correct? It will, so instead of 0.2 on the delta will, it will say the delta W may be 0.08 milliseconds. So 1.569 plus 0.8 this one. Correct? So 9, this is going to be. So now new pulse width will be this. Okay. Hello. கொஞ்ச நேரம் கழிச்சு கிளாஸ் கூப்பிடுறேன். Okay, so now he is injected. This is a closed loop. So what it means, the airfield is a closed loop controller will be continuously varying the base pulse width. Base pulse width is for the particular throttle. 3 zone RPM as a 4 zone RPM 10% throttle, it is 1.569 millisecond. That is using lookup table. Correct? That is called as open loop controller. Correct? Or feed forward. That is also called feed forward controller. That is called as feed forward controller. Feed forward controller is an open loop controller. Based on engine speed and throttle position, we select the base fuel injection, which is already stored in this one. Then fuel is that much fuel is injected inside the engine. Then the actual airfield ratio is measured. If you lean average, accordingly, the closed loop controller will add or subtract. Correct? This controller will add base pulse width plus or minus delta W. The delta W is computed by the closed loop airflow. So accordingly, the fuel pulse width will become from the original pulse width add or more. So you will be always able to maintain what is the 15 point is to this one. So this is how it works. I stop here. Next class we will see about the diesel engine, and then we'll go to steering system. Okay. Electronic.
Sir, I have one
steering.
doubt.
Yes, please.
Sir, can you go to previous slide in that equations are there?
Yeah.
Say next. This is open loop or this is closed loop, sir?
This is closed loop.
Okay.
Because
This is
I will
also-
see you in the model you have EGO, no? EGO also is this equation can be EGO part also, no?
Okay, okay. So the same way what you explained now,
Yes.
it also works in the same way.
Yes.
Okay.
So this
we
is a
have-
modeling. This is for mathematical modeling and simulation.
Okay, understood, sir.
Okay.
Open loop is also there, sir?
Open loop lookup table, no? See,
Okay,
here
lookup
if you
table
see,
only.
no, you can do that.
Understood.
If you remove this EGO sensor, it become open loop.
Okay, understood.
If you remove in the mathematical equation, remove the EGO sensor dynamics. Correct?
Right, right.
Then
Yeah,
it is
yeah.
open loop
In that case, only the throttle position will decide the air fuel ratio.
throttle position, wall dynamics, the fuel dynamics, the fuel puddle evaporation, this one, correct? Only
Okay.
throttle dynamics going to decide.
Okay. Right, right.
Okay. And stop here. We will see tomorrow, 8 o'clock.